Assalamu alaikum dear viewers, Shoaib and Dayo is here with the new lecture of the power factor series, and today we are discussing the disadvantages of the low power factor. In the previous videos we have discussed what is the power factor. Is the cosine phi angle between the voltage and current is called power factor, or it is the ratio of the resistance over impedance is called power factor, or it is the ratio of the active power true power over the apparent power is called the power factor. So power factor plays an essential and important role in our electrical power systems. So there where the value of the power factor is to be vary from the 0 to the unity. Now we are discussing the disadvantages of the lower power factor. Means what are the main disadvantages when the power factor is low. So as we know, the power for formula for calculating the power in a single phase supply is the P is equal to VI cosine of phi. Here cosine phi represents the power factor. Now from this equation, if we are find out the line current of the single phase supply, so it will be the power divided by the voltage and the power factor. So from this relation, the line current or the current has the inverse relationship with the power factor. So if the current is greater, then the power factor is lower. So obviously at the lower power factor, if the current is greater, so I square R losses are greater. If the I square R losses are greater, so it will the terminal voltage of the equipment or the electrical machines or the electrical appliances will be low. So it may cause the poor efficiency of the electrical appliances or electrical power system. So formula for calculating the power in a 3-phase supply, it will be the under root 3 VI cosine of phi. And again here in the from here if we find out the current in a 3-phase supply, so that will be the power divided by under root 3 V cosine of phi. So now it is clear from the expression number 1 and expression number 2 is that at the amount of the fixed power and the voltage, if the voltage is constant and the power is constant, at the fixed power and the fixed voltage, the load current has the inverse relationship between with the power factor. So if the current is greater, the power factor is lower, and if the power factor is higher, then the current will be lower. So lower the power factor, higher the load current, and power factor is less than the unity because of the following disadvantages. So always the power factor, if there is an we have electrical in our electrical engineering, we have to our main motive is that to maintain the power factor close to the unity. But if the power factor is not unity and power factor is lagging, so here there are the following disadvantages of the lower power factor. Number first is that large kVA rating of the equipment. As we know that all electrical machines are alternators, synchronous machine, induction machines, transformers are constructed are designed on the basis of the apparent power. So electrical machinery, alternator, transformer, switch gears are always rated in the kVA. Why kVA? Because the power factor of the load is unknown. We don't know that which type of the load that we are going to connect with the any electrical machines. So the power factor of the electrical machines is depend upon the load. So obviously all these electrical machines are designed on the basis of the apparent power, not in the true power, because in the true power the power factor that we are going to include, but on the basis of the apparent power, here it is excluding the power factor if we are, so due to the because the load is unknown, so that's why the power factor we are not including. So here in this relationship, the kVA apparent power is the kW over cosine of phi. So here you can see the relation. The apparent power has inverse relationship with the power factor. So if the machine apparent power is greater, or at the lower power factor, the size of the equipment, and it will be bulky in size, its costs will be very expensive, so at the lower power factor. So it's our main motive to make the power factor higher. When the power factor is higher, the equipment size will be low. If the size will be low, obviously the cost will be low. So first disadvantage is that the large kVA rating of the equipment. So if the kVA equipment of the of any electrical machines, either it is alternator, transformer, induction motor, is large, its apparent power is large, obviously the power factor will be low. So for designing any electrical machines, we have to keep one thing in our mind, that it should have the higher power factor. So if there is a higher power factor, the size of the equipment will be low, because due to the apparent power will be low. Second is that greater conductor size. If the conductor size is greater, it can carry the more amount of the current. So if it can carry the more amount of the current, obviously the I square R losses will be increased. So here, to transmit and distribute a fixed amount of the power at the constant voltage, obviously the system voltage is constant. So if we have to find transmit our electrical power through transmission line and distribute the electrical power at the distribution side, so the conductor will have to carry the more current at the lower power factor. Obviously from here you can see the power factor has inverse relationship with the current. If the current is more, power factor will be low. So amount of the current which is to be carried by the conductor is more when the power factor is low. When the power factor is high, then the amount of the current which is to be carried by the cables or the conductors will be low. So here we have a case. So if there is a lower power factor and the current which is to be carried by the conductor is greater, obviously the size of the conductor is increased. Obviously the size of the conductor, cross sectional area of conductor or width of the conductor is increased. Now we are considering the two cases over here. Single phase induction motor, okay, which is operated on the unity power factor. Let's see an example, and cosine phi over here in the second case is the 0.8 power factor. Now the power P is 10 kilowatt and voltage is 250 volt. Now here how you can find out the line current of the induction motor in the single phase? P divided by V cosine of phi. Now here power is the 10 kilowatt and cosine phi is 1, because here the power factor is unity. Now what will be the current? 40 ampere. In the case of the unity power factor, the line current is the 40 ampere. And here if the power factor is low, due to the induction motor operation, it draws the lagging power factor from the supply. So here the 0.8 power factor we are choosing value. So put the value of the power factor and all the parameters in the formula. P divided by V cosine of phi. So here P is the 10 kilowatt divided by 250, 0.8 is the power factor. Here is it was the unity, here it is the 0.8. So this is the 50 ampere. So from here in this relation, if the power factor is low, current is high, and here the unity power factor, the current is 40 ampere, and here the power factor is 0.8, the current is 50 ampere. Means if the motor is worked at the lower power factor at 0.8, the cross sectional area of the supply cables and the motor and the conductors would have to be based upon the current of the 50 ampere. Means if the motor is operated at the 0.8 power factor, obviously we have to design the system, we have to design the cables, and we have to design the conductors on the basis of the 50 amperes instead of choosing the 40 amperes current. So instead of 40 ampere which would be required at the unity power factor, we have to design the conductors and the cables diameters and the selection of the conductors on the basis of the 50 amperes. Means it is clear from these from this case is that if the power factor is the 1, the current is 40 ampere, and if the power factor is 0.8, the current is 50 ampere, and kept the voltage and the power is kept constant, and if you are varying the power factor, so the line current will be increase or decrease with the increase and decrease of the line current. So this was the greater conductor size. Means if the power factor is low, the current will be power factor is high, the current will be low, and if the power factor is low, the current will be high. Number third is that large copper losses. So at the large current the power factor is low, and then it causes the more I square or losses, power loss in all elements of the supply system, results in the poor efficiency. Simple. If the current is high, for example in this case if the power factor is 0.8 and here current is 50 ampere, so here in the 50 ampere case the I square or losses, power losses are maximum in comparison to the unity power factor case where the current is the 40 ampere. So if the current is if the current is increased, power factor is low, and if the power factor is low, then due to the increase in the current, I square or losses are increased, power losses increase in all elements of the power system, results the poor efficiency of the power system. Number 4th, poor voltage regulation. So the large current at the low lagging power factor, okay, causes greater voltage drops in alternator, transformer, transmission lines and the distribution lines. So if the current is large, again if the power system is non-linear in behavior, so if the current is high, the power factor is low. If the power factor is low, the obviously the I square R losses are increased. It will also cause the volt drops in the power system. So resulting there will be a poor voltage regulation occurs on the distribution side and on the consumer appliances. So always we know that the voltage variation permissible is 5 to plus minus 5 to 10%. Okay. So if that results in decrease in the voltage, if there is a low lagging power factor and the current is high, the voltage is reduced, and which is reduced at the supply end, and which also impairing the performance of the utilization devices. So to maintain the voltage at the consumer side due to the low lagging power factor because of the poor efficiency, so voltage regulators are being installed to maintain or to stabilize the voltage at the consumer premises. So this was the disadvantages of the power factor. First, that was the large kVA equipment size. So if there is a power factor is low, the kVA equipment apparent power of the equipment is high. Second, that is that if the power factor is low, the current is high. If the current is high, I square R losses will be more, and also it will carry the more amount of the current within the conductor. Obviously the cost of the conductor will also be increased, so obviously power factor will be low, the cost will be also increased, so it will results in the poor efficiency, it will results in the poor voltage drops in the systems. Okay. And now we are discussing some causes of the low power factor. So power factor of the whole load in a supply system is lower than the 0.8 due to the certain reasons. Like most of the our loads are the like in the motors are the AC motors, induction types, it may be the 3-phase or the single phase induction motors. So they are work very at the very light load, they are working on the 0.2 to 0.3 power factor, and if if the load is to be induction on the induction motor is increased, so its power factor is gradually increased from the 0.8 or up to the 0.9 at the full load. And second one is that arc lamps, electrical discharge lamps, industrial heating furnaces are also cause of the may cause the lowering the power factor of the our power systems. And also our non-linear devices like power electronic converters, our thyristors and our non-linear loads are also cause deterioration of the power factor. So this is also another cause of the causing the lower power factor in the power system. So this was the whole lecture regarding the disadvantage of the low power factor, so in which we have discussed the relationship between the current and the power factor. It has the inverse relationship at the fixed power and at the fixed voltage, and also we have discussed the large kVA equipment. Through this expression, the power factor has inverse relationship with the apparent power, because all the electrical machines are designed on the basis of the apparent power on the VA power. So because of the power factor of the system is unknown, because the load is to be power factor is to be depend upon the load. Third, the case was the greater conductor size. So at the amount of the fixed power and the fixed voltage, conductor will have to carry the more current, and obviously the size of the conductor will increase at the lower power factor. And third, that was the large copper losses, and at the fourth, that was the poor voltage regulation. So this was the lecture. I hope that you have enjoyed today's lecture, and please subscribe my YouTube channel Shoaib Ahmed Dayo for more informative videos related to the electrical engineering area. Thank you.